Okay, so we're going to continue what ought to be still a review for all or most of you guys. Um, Stuff that probably covered in calculus and um, and touched on in physics, I suppose. Um, but it's going to, so I'm not going to be dealing with a comprehensive review here. So vector calculus is a large subject, and I'm just going to be focused on the concepts and ideas that we're going to be using in this course. So, um, so what the what we're going to be dealing with here is uh, functions that return vectors. Okay, so they're called vector valued functions, or for short, just vector functions. And they take a set of parameters. In our case, it's almost always going to be a single parameter, but in general, they could be, you could use several numbers to define the vector. But the point is, it takes a parameter or set of parameters and returns a function. I'm sorry, returns a vector. Okay, and the biggest example would be what we're going to be dealing with is the position vector. All right, so the position vector and its derivatives, but the position vector so is often expressed as a function of time, and in Cartesian coordinates, it'd be given by a set of scalar functions multiplied by their vector components, or the basis vectors. Okay, and so what you have here so you have, like, at time equals 0, you might have a vector here. So this would be, say, r at t0. Okay, and then maybe at t1 you could have a vector, another vector, and then maybe even a third vector or something like that. So at r at t equals 2, maybe you get a third vector, a different vector. So as t changes, the vector changes. And so the vector itself, it could trace out, say, a path. In this case, so the path might describe the path of an object where its position is given by the position vector at each time. So as t increases, the particle in this case might follow this trajectory, which at time t, the position vector points to that position. Okay, so that's pretty straightforward. There's also another parameterization that we're going to use, and that is like the arc length along the curve. So we could use, that's usually given the parameter, it's given the symbol s. And it's basically the same thing, it's just parameterized differently. So in cylindrical, or I'm sorry, in Cartesian coordinates would be given like this, and S so roughly given the same curve, this might be when S equals 0. And S is defined as sort of the arc length along the path. So S would be defined as this length of the path along the path. So it's not just the difference between locations. So this might be the position vector when S equals, say, well, it's some value S. And so we could parameterize it this way, and there's certain benefits to doing that. And so S is related to the more kinematic variables that we're going to be dealing with, the velocity of the particle and time and everything in this way. So S is the integral of the magnitude of the velocity over time. So S is related to the path itself in this way, and so taking the derivative S dot is just equal to the magnitude of the velocity. Okay. So now that we have a vector valued function, we need to be able to, what we're going to be doing in this course is taking their derivatives quite a bit. So it follows very closely to the definition of derivatives with just, scalar functions you're used to. So I'm going to be using this notation. So if it gets an arrow and a dot, if it's the derivative with respect to time. Okay, and that, if you remember from the definition that you learned in calculus, so in this case, these are vectors though, but we already learned how to add and subtract vectors. So what we'll have here is, say we have a path, and then at time t, we have this position vector, and then at time t plus h, we may have moved along to this point. And if you remember, the difference in vectors is essentially just connecting the tips. So t minus h, r of t minus h minus r of t looks like this. But then this is divided by some small number h. So we wind up with a scaled version of the connection of the vector that connects the tips of the two vectors in this formula. So this right here that's what this vector is right here. Okay, and then as h approaches 0, so we take the limit as h goes to 0. So in that case, this vector slides over and gets closer and closer and closer to this vector. At the same time, it's being divided by the step size h. So the magnitude roughly stays equivalent, or roughly stays the same. It's not, it changes somewhat, but it approaches some limit. And as long as h is small, the magnitude isn't going to change a whole lot, because as the magnitude of the top decreases as these two vectors become close to one another, they get scaled by the step size in t. So the magnitude roughly stays the same, but see how this thing is basically cutting the corner in the curve, but as h approaches 0, this approaches the tangent line, so that as h goes to 0, r of t plus h gets closer to r of t, and this ratio basically defines a line that's tangent to the curve. Okay, so this would be at time t, this would be the time derivative of the position vector. It becomes the tangent vector of the curve. Okay, it becomes a vector that's tangent to the curve at time equals t and at position r of t. So this would be position r of t. So position r of t, r dot t is tangent to the curve, to the path at r of t. Okay, so, okay, that's great. In terms of Cartesian coordinates, in terms of the Cartesian coordinates, it's pretty simple. The time derivative with respect to time, the time derivative of the position vector is just the time derivatives of the individual components. Now, it's a little bit more complicated in certain coordinate systems, and I'll get into that here in a little bit, but this is going to be equal to the time derivative of, so it'd be like Rx of times I plus RZ, or Y of times J plus RZ times K. Okay, now there's remember the concept of the product rule from calculus. So to do this, we have to take the derivative of each term. However, each term is a product between a scalar and a vector, so we have to apply the product rule in each case. So the product rule applied here would be Rx, the time derivative of Rx times I plus the plus Rx times the time derivative of I. Okay. And now likewise for Ry and Rz, or the y and z components. So in Cartesian coordinates, we have this where the time derivatives of these vectors are 0. They remain constant throughout the space and for all time. They're constant. So these all wind up canceling out. So we get the simple expression of just taking the time derivatives of each of the components. Okay, and that's because the time derivative of each of the basis vectors is 0. This is only true, so this is true in Cartesian coordinates. When we get into other coordinate systems, this will not be true. And so it complicates greatly, not greatly, but it complicates the taking of the derivative of a vector function. So this, it turns out, is the velocity of the particle. So if the position as a function of time is given by this expression here, we take its derivative, that gives us the velocity vector. So the velocity vector is just the time derivative of the position vector. Likewise, the acceleration is just the time derivative of the velocity vector, which is the second derivative of the position vector. Likewise, and that's, again, because the basis vectors are constants. They don't change direction, nor do they change magnitude. Okay. So I'm just going to write down some differentiation rules. Okay, so for taking the derivatives of vector functions, there are rules that are essentially the same as what you should have, you remember for scalar functions. Okay, so if we take the time derivative, or we take the derivative of a vector sum, well, just to be explicit, I'm going to be a little bit loose with these. Sometimes it's implied that everything's a vector, or a function of time. So if I have two vectors, u and v, both of them are functions of time, and I take their derivative, that's just going to be the sum of the derivatives. If I take the derivative of their sum, that's going to be equal to the sum of the derivative. So that's just going to be okay. Likewise, if I take the scalar product, the derivative of the scalar product with a constant, so c times a vector function, that's just going to be c times the derivative of the vector function when c is a constant. Okay. If c is not a constant, so c itself is a function of time, then we apply the product rule just like from ordinary calculus. And so take the derivative of the first times the second value. And then we have to add into that the first times the derivative of the second value. Okay. So as you can tell, this is just kind of a special case of this, where f dot is 0. And then, so t is a parameter here. It's a very common parameter. It usually goes for time in our case, but this could just as easily have been s. So we could be taking these function or these derivatives with respect to s, and the same rules apply. So let's see here. So the dot product. So if I have if I'm taking the time derivative of the dot product of two different vector valued functions, the product rule applies here as well. So that's going to be the derivative of the first dotted with, using the same operation, so dotted with the second. So dot that with the second. and then I have to add on the dot product of the first vector with the time derivative of the second. Okay. Same for the cross product. So I have two vector valued functions. I take the cross product, or I take the time derivative of the cross product, and that's just going to be the same thing, except instead of applying the dot product, we're going to apply the cross product. So derivative of the first crossed with the second, and I got to add the first vector crossed with the derivative of the second. And then we also have the chain rule, if you remember the chain rule. So now I have a composition, a composition of a vector value. So I have a vector valued composition. What I mean, what's a composition here? So I have a vector that's defined by some function, takes as its argument some other function of t. So I have a function of t that is being supplied as the argument to the vector valued function. And in that case, the standard chain rule, if you remember the chain rule, applies. So first thing I got to do is take the derivative of the vector function. So I take the with respect to its argument. So I take the u, I want to use a prime, and we take u prime at f of t, all right, and then we've got to multiply that by the time derivative of f. Okay, so the prime implies that it's a derivative of some argument other than time. It's just the derivative. Don't get too wrapped around it. It's just the derivative of the function u. Okay, we'll be doing plenty of examples. Oftentimes it'll be switching between the s parameter and the time parameter, maybe something along those lines. Don't get too. It is sort of the intuitive understanding. So you take the derivative of u, you take it at the value of f of t, and then you got to multiply that by the rate of change of f of t. That's just the chain rule. Okay, and so let's deal with cylindrical coordinates. So cylindrical coordinates. I have, rather than giving the x, y, and z locations, I give the distance. On the xy plane, I give the distance from the origin in terms of x and y. on the xy plane, and then apply a z coordinate as well. All right, so the z coordinate stays the same, but the x and y are replaced by the distance from the z axis along with the angle theta of the position vector projected onto the xy plane. All right, so in sort of mathy terms, the coordinate r, which is just the length of the position vector, or the length of the position vector, is just the magnitude of the I'm sorry. So r is not necessarily the length of the position vector. It's the length of the position vector projected onto the xy plane. So we're neglecting the z coordinate here. All right. I'm not trying to be. Most of you guys understand what I'm talking about. So I'm not trying to be. I'm not trying to contradict your understanding. You know what I mean? This isn't anything new. Okay. And then the z coordinate is just equal to the same as the z coordinate. Now, it's going to be useful for us. We have a different set of basis vectors that we define things. So we have the u, the book uses this notation. U sub r is the basis vector that's projected along the r coordinate, as well as u sub theta, the unit vector u sub theta, which is orthogonal to u sub r, which, perpendicular to u sub r, and points in the direction of increasing theta. All right. So we can express these basis vectors in terms of the standard basis vectors I, j, and k. So u sub r is just, this is a powerful technique for defining things. So for defining vectors where their their angles, but not necessarily their magnitude or something along those lines, you can kind of decompose it into the direction and magnitude based off of the Cartesian basis vectors. So u sub r is straightforward. It's projected onto the xy plane, so it's always going to be just a weighted sum of I and j, and the weight is cosine of theta, so it changes as a function of theta. As we move around in theta, u sub r changes direction, right? However, if we move around in r, u sub r remains constant. So it just moves in and out, but there's no, its magnitude is always 1, and its direction remains constant as we move in and out in the r direction. Likewise for u sub theta, as we move in and out on the r, it remains constant. Its magnitude stays 1, and it's always perpendicular to r and always pointing in the direction of increasing theta. So it remains constant as we change r. All right, and it's always perpendicular, and it's always pointing counterclockwise. And so we can define it So these are the basis vectors and cylindrical coordinates expressed in terms of the basis vectors in Cartesian coordinates. All right. So the position vector. The position vector in cylindrical coordinates is just the coordinate r times u sub r plus the z coordinate times k, right? So it's just the value r times u sub r. So all of the position is encoded in this u sub r basis vector, right? The angular information is encoded in this basis vector here. All right. So we can take the time derivative in order to calculate the velocity. That's just the time derivative of the position. So we have a product here, so we got to take its, we apply the product rule, so we'll have r dot u sub r plus r times u sub r, the time derivative of u sub r. Plus z dot k, and then again z k dot, but k dot is constant in this case. So there's no, I'm not going to include that. So everything here is straightforward except for this. Like, how do we calculate u sub r, t, time derivative of u sub r? So this is an instance where we're going to apply the chain rule. So u sub r dot is equal to, so that is the ddt of u sub r. It might be a little more easy to understand here if I do it like this. And that, if you remember, we can sort of reverse the chain rule. So this u sub r is a function of theta. Theta is a function of time, usually. So we can decompose that into and so shorthand for that would just be theta dot times the u sub r d theta. All right, so we've made a little progress. U sub r is defined as a function of theta, so we can take this derivative. And so the derivative of cosine is negative sine. Derivative of sine is cosine. But look at this. That's just another way of writing u sub theta. So this, so the time derivative of u sub r is just u sub theta. And that makes sense, right? As, no, I'm sorry. It's the theta dot times u sub theta. So that makes sense, because u sub r only changes direction, and its direction is always equal to the theta coordinate. It's roughly, or it's related in this way to the theta coordinate. So intuitively, you can kind of make the connection, all right, just from the picture. So then the velocity in terms of the coordinates is given by, in terms of the coordinates in velocity, or in basis vectors, it's given by this expression here. Now likewise, we do have to do a similar thing for the acceleration. So the acceleration is just the time derivative of the velocity. And so we're going to calculate, component by component here. So we have a derivative of the first times the second plus the first, I let this drop off, first times the derivative of the second. Likewise for the second term here. So we got three variables here, so it gets a little bit funky. So so derivative of the first. So I'm going to sort of group them this way. Times the second. Sorry about that. There should be a plus sign. So the derivative of this, so as far as this term is concerned, so the derivative of the first times what was in the second, plus the first, which is r, times the derivative of the second, but this time I got to apply it again. I got to apply the product rule one more time. So here I'm going to take the derivative of the first times the second, plus the first times the derivative of the second. And then likewise, this z component is just along for the ride because it's all constant. We don't have to worry about all this weird stuff. So everything here is known except for this. So we have to basically perform the same thing we did here for the time derivative of u sub theta. But you can kind of tell what's going to happen here, right? As theta increases, the tip of u sub theta is going to turn in the direction towards the origin, right? Well, towards the origin is going to be negative u sub r. But just to be explicit about it, let's go ahead and calculate it. So u sub theta, the time derivative of u sub theta is equal to the derivative of u sub theta with respect to theta times derivative of theta with respect to time. And that's just, again, theta dot times du theta d theta. And again, we can calculate that. So that just comes out to and if you notice, that's just negative u sub r. Okay, so the acceleration, let's try to collect terms here. So or expand out the stuff we know. Remember, u sub r, that's just u sub theta. The time derivative of u sub r we calculated previously, so that's u sub theta. the time derivative of u sub theta is just, we calculated this here, so the time derivative of u sub theta is theta dot, which I'll just go ahead and put that in here. So theta dot times derivative of u sub theta with respect to theta, which is just negative u sub r. And then the z dot comes along for the ride. All right, so let's group them all up into u sub r's and u sub thetas and stuff. Sorry, so collecting terms here. So we have, so the u sub r terms, we got r double dot, all right. And then we have a negative r theta dot squared. So theta dot times theta dot, and that's multiplied by u sub r. So we got this term out of the way. And now we have a bunch of u sub theta terms here. So oh, there's a theta dot here that I left out. See that? So let's see here. So u sub r, the time derivative of u sub r is theta dot times u sub theta. Okay. And in fact, I'm going to write that. So okay, and here, so it's negative theta dot times u sub r. Okay, so I got the u sub r terms pulled in here. Now it's the u sub theta terms. I got two r dot theta dots and an r times theta double dot here. And then so the z component is just a time derivative of this. So I was leaving off a little dot there. So this is double dot. Anyway, this winds up being correct.